Well, hello, members of 7th grade Blue. I hope you are doing well. Today we're going to look at a little bit of geometry. However, it's kind of moving us back into that scaling effects that we've seen. We're first going to kind of talk about, well, what are similar solids? So what I want you to do is write this down. Similar figures or similar solids have the same shape, and that their corresponding dimensions are proportional. Go ahead and write that down, because what we want to look at is situations that are similar and ones that aren't. So if I drew a cylinder in this sort of fashion, and I drew a larger cylinder like so, and I named out some dimensions. Let's say the height of this one is 3 and the height of this one is 6. It's not perfect. Just do your best. And then if I name the diameter of the base here as 4, call it 4 miles, 4 feet, 4 inches, I don't really care. And then this one is 8. That would be a pair of potentially similar solids. Let's look at another pair of solids. So let's say I had the exact same cylinder as the first one I drew, dimensions of 3, diameter of the base of 4. And then this one, the diameter of the base is still 8, but you see that the height is different at 4. And so what it talks about is that the corresponding dimensions are proportional. So we do see that the bases in both of my little pairs, this one, the 4 and 8, and then over here, the 4 and 8, those are exactly the same. We're not really comparing the green against the red, though. We're comparing the red against the red. So if I look at the 3 and the 6, I notice that all the dimensions are basically doubled, or they're half from the big. And that would make for a scale factor of 2. And because that scale factor can be drawn out through the whole thing, then I'd have to say a certain thing, which we'll say in just a moment. However, here I see a scale factor of from 4 to 8, clearly 2. But when I compare my 3 to 4, that is not a scale factor of 2. And because they don't have the same scale factor, we couldn't say that their dimensions are proportional. So the first pair here is clearly a pair of similar solids. Whereas this one, because they don't have the same scale factor moving throughout their dimensions, will be not similar. And again, it's not really what this lesson is about, but we haven't really talked about similar solids. We've talked about similar figures and things, but the same sort of ideas apply. Corresponding dimensions are proportional. But let's really get into the meat of the lesson here. So they're clearly not similar. Write this down. An architect builds a scale model of a building she is designing. The scale is 1 inch to 5 feet, and we actually have a few questions to deal with here. The first is, what is the scale factor from the model to the building? Well, they've given us a legend here, this 1 inch equals 5 feet, but notice how those have mixed measures. So probably the easiest way to deal with this, I would imagine, is to take that 5 feet and translate that into inches. We should know 5 feet, as a basic fact, is 60 inches. And so it says, what is the scale factor from the model? The model is the 1 inch, and the building is the 60 inches. And so what I want to think about is, okay, so from the model to the building, the scale factor is how much am I multiplying? And then clearly, like, this kind of cancels out to be that I have a scale factor of, yeah, you guessed it, 60, right? Now we're going to use that scale factor because what we've been seeing lately is that how does scale factor affect things like perimeter? It doesn't. Area? It does. And volume? It does even more. So the next question asks about the surface area of the building, and they want to know how many times that is of the model. So just not too long ago, we thought about this. What is the ratio of areas for similar figures or similar solids? And we determined that it's the scale factor raised to the, do you remember? Good, raised to the second power. So if I have a scale factor of 60, that raised to the second power would be equal to 3,600. So the surface area of the building would be 3,600 times that of the model, right? The surface area is 3,600 times the model. That's big, right? Well, you think that's big. What about volume? What about the volume of the building and the volume of the model? Like, let's say I was going to fill the model with sand. How much sand would I need for the building? Well, whatever the amount of sand I needed for the model, I need a lot more for the building. Because remember, the ratio of areas is the scale factor squared. What is the ratio of volumes? Well, hopefully you remember, because it wasn't too long ago that we wrote down that the ratio of volumes will be the scale factor, not squared, but cubed. So that means that I'd have to take the 60 and cube it. Well, I already know 60 squared is 3,600. If I multiply it by another 60, thus cubing it, I'd tag 0, 0, 0. 6 times 6 is 36. Carry the 3. 3 times 6, 216,000 times that of the model, right? So again, your book seems so concerned about you coming very comfortable with these. We're going to do another problem, and then we're going to have a posting opportunity for you. Please write this down. It says the volume of a model car built to a 1 to 20 scale is what fraction of the volume of the car? So again, they're talking about volume, which we just dealt with, so that should be helpful. And we also have a scale here. So a 1 to 20 means that I have a scale factor of what? Good, of 20. Now, when we think about volume, we know that we're going to think the scale factor raised to the third power. So if my scale factor is 20, 20 to the third is, well, I know 20 squared would be 400 times another 20. What will that be? Well, 4 times 2 is 8, and I tag 3 zeros. So that's 8,000. But notice how they're asking. It's slightly different than the last question, right? The last question was, how many times bigger is the building than the model? But notice what they say here. It says, the volume of the model of the car is what fraction of the volume of the car? So in this case, I'm not going to answer 8,000 times or anything like that. What I'd answer is that the volume of the model of the car is 1 8,000ths. And that would answer that question. Yeah. So no more writing. However, we do have a opportunity. There's no need for a cover-up tool. I do need you to open up your book to page 713. And you don't need to cover up, just don't turn the page, right? And looking at example 2, it starts off by saying, to create a cast. I really want you to take the opportunity to read through that. There's a lot of words going on. Think through it. Think about what we've been talking about in regards to scaling effects. Take your time, write it out. I want you to do this problem. You should do it directly in your notes and pencil. And then I want you to post. Now, I know when we post, it's so questionable, like, especially if the twins are involved, right? So one posts and then the other posts directly after. Well, I mean, were they communicating? And if they weren't communicating, what about someone else who's just like, well, I'll just wait till someone posts their answer and I'll copy it down. All of these would not be beneficial to you. I want you to work it out on paper. I want you to do your best and then post on Google Classroom. It doesn't matter if you're first. I want you to kind of explain your reasoning behind. And that'll be a good opportunity for you. Okay. Now we do, because this is Monday and we did homework 107 on Freya's Day, we do have the regular split. So HW 107, 108, we are on track for finishing this book, which makes me so happy. I'm proud of all your efforts. Thank you very much. Let's keep it working. Let's finish strong. Take care. Bye.